Okay, to be continue consenting, continue. Okay. All right, now I also see the attendees. Okay, panelists is just the 4 of us, but then there is attendees and the number is now at 43 and so on.
All right.
Okay. All right, so I think we can get started. So we'll be on time. Welcome everyone. This is the keynote lecture number 4 of ISBA 2021. My name is Marina Vannucci, and I will be chairing the lecture today. We'll take questions as I think we have been doing at the conference. So just throughout the talk, you can type your questions in the Q&A, and then we will read and answer all the questions at the end of the talk. Okay, so our keynote speaker today is Professor Leonhard. He's a full professor of biostatistics at the University of Zurich, and he's also the head of the biostatistics department there. He got his PhD in 1997 at the Ludwig Maximilian University of Munich. He spent some time in the US at the University of Washington, and then he was a lecturer and senior lecturer in the UK at Imperial College and Lancaster University. He was then associate professor for 4 years back at the LMU in Munich, and he has been with the University of Zurich since 2006. He's currently an associate editor of biostatistics, applied statistics, and statistical modeling. His current methodological research interests are in the statistical aspects of reproducibility and replicability, infectious disease data, and Bayesian inference in general. He's particularly well known for his contributions to epidemiology, spatial epidemiology, and of course, Bayesian statistics. Today, he's giving a lecture, a keynote lecture on the statistical assessment of replication success, a case of reverse Bayes. Welcome, Leo.
Thank you, Marina. I hope you can hear me and you see the pointer.
Yes.
So it's a great honor and a great pleasure for me to give this keynote lecture. I'm very delighted that I can talk about recent work that I've done together with a bunch of people, I will mention at the end, on the analysis of replication studies, and I want to make the case for reverse Bayes in this setting. Okay, so this is my outline. I start with a fairly brief introduction to the concept of replicability and also to the reproducibility crisis, as it's called, then introduce something I proposed a few years ago, what's called the skeptical p-value. But of course, at a Bayesian conference, you cannot end with the skeptical p-value. So there's also more recent work on the skeptical Bayes factor that I would like to talk about, and then a brief discussion. Right, so replicability. There was a session already this week on the reproducibility crisis in science, and replicability is a big part of it, or missing replicability, if you wish, because replicability is crucial to the credibility of science. And in the last years, large-scale replication projects have been conducted in various disciplines to investigate how replicable published research results are. And the idea is always that you conduct an independent replication study, independent from the original study, in order to confirm the original result. And you see this cartoon here at the bottom, basically in the first row. There's somebody who has a plan, maybe a design of an experiment, then the experiment is conducted, data are analyzed, and then a paper is written up. And then in the second row, basically we repeat this process in the other direction. So we take a look at the paper, try to reproduce the experiment, do it again, analyze the data we obtain again, and publish the result of this replication experiment. Now, a particularly famous replication project was the one in psychology. It was entitled Estimating the Reproducibility of Psychological Science, but perhaps the better title would have been The Replicability of Psychological Science. And that was published in 2015. And actually similar replication projects have been published in the last years in social sciences, in experimental philosophy, in experimental economics, and also in cancer biology. That one was led by the OSF, the Open Science Foundation in the US. And the outcome of the psychology project is shown here on the right. So in that project, 100 studies have been included. And this figure gives you the replication effect size versus the original effect size. And all the effect sizes from the different studies have been streamlined to a common scale, to the correlation scale. This is why the scale runs here from 0 to 1 in the original experiment, because they have been all oriented to be positive. And then in the replication effect size, it goes from -0.5 to 1. And you see the typical distribution of such projects, that some of the studies are on the diagonal. So that means, the replication effect size is roughly the size of the original effect size. But actually, the large majority of studies is below the diagonal. So that means the replication effect size is smaller than the original effect size. It can be considerably smaller. It can be even in the other direction. And what's also shown here in colors is whether or not the replication study was significant in conventional terms. So 0.05, two-sided. So if you think about how to analyze such data, it's useful to have a benchmark. And I think a useful benchmark is what's called the two trials rule, which is used by EMA and FDA in drug regulation. And the two trials rule requires at least 2 adequate and well-controlled studies, each convincing on its own to establish effectiveness. And this is essentially one method that is also applied in the analysis of such replication projects, that they check whether the replication study is significant and the original study is significant, and whether the replication effect is in the same direction as the original effect. Okay, so in kind of conventional statistical language, they want 2 statistical tests significant at the 5% level. And as usual in pharma, they prefer to work with one-sided p-values. So that's also what I do here. So we want the one-sided p-values to be smaller than 2.5%. So that's the usual pharma standard to take into account effect direction. Obviously, a deficiency of this approach is that effect size is not taken into account, at least not directly. And also this, what I call double p-value thresholding, is a questionable way to quantify the available evidence. You can easily construct, counterexamples. For example, 2 studies with p, one-sided p equal 0.024, they would pass the 2 trials rule. But suppose one study is perhaps 0.026, but the other one is 0.001, then that would actually not pass the 2 trials rule. So, but still, it's a standard in drug regulation, and it's perhaps something that we should use as a benchmark. Well, here's an example, I think, from the social science replication project, which shows effect estimates and 95% confidence intervals. And I also show this to introduce my notation. So left is the original study. You see an effect size of 0.4, one-sided p-value 0.011. And on the right side, you see the replication result, effect size 0.15 and one-sided p-value 0.004. So both p-values are sufficiently small to pass the 2 trials rule. So from that perspective, that would be a successful replication. To introduce a bit more notation, N is the sample size, O stands for original. So the original sample size was 36. The replication sample size NR was 306. And likewise, we have theta hat, which is the effect estimate, sigma is the standard error, and P is the one-sided p-value. Now, you may wonder, well, is this really a successful replication? Is this how I would quantify success? And actually, there's no consensus in science what to do to flag a study as a success. And a second approach that is quite often used is a meta-analysis. And as you know, meta-analysis is actually nothing more than just standard forward Bayes. So basically, we combine the evidence from the 2 studies into a combined effect shown here in the middle, the meta-analytic effect, which is 0.17. And as you can see from the confidence interval, this is also sufficiently far away from 0. So also the meta-analysis would flag this as a successful replication. Now, I want to ask the question, is this really a successful replication? And I want to introduce 2 things, 2 quantities, which will be important for the rest of my talk. One is what we call the relative sample size. So that's the sample size of the replication study compared to the original study. And as you can see, the replication sample size is much larger than the original sample size, is actually by a factor of 9.2 larger. That's the relative sample size, which we call C. And at the same time, the relative effect size, so that's the effect estimate replication to original, is 0.38. So you see this already in the figure. The effect estimate in the replication studies is considerably smaller than in the original study. So there is a substantial decline in effect size. There's a shrinkage of 62%, 1 minus 0.38, which makes you wonder if this is really a successful replication, because as we all know, it's not enough just to look at p-values. We should also look at effect sizes, and if there is such a substantial shrinkage, then you may wonder if this is really successful. So imagine the original study is maybe a COVID-19 vaccine study that gave you 95% vaccine efficacy, and suppose the replication study is also significant, but maybe vaccine efficacy has dropped just to half of that, then I guess most of you would not consider this to be a successful replication. Okay, shrinkage is an issue. And how do we bring shrinkage into the game here? So let's first look at some summary statistics in those 4 replication projects. By the way, the data that we analyze here is all available in our R package replication success that I will briefly mention at the end again. So if you look at the summary statistics, those are medians and first and third quartiles of the relative sample size here in the second column and the relative effect size in the third column, then you see, well, the sample size has mostly increased, and so we have large relative sample sizes, large sample sizes of the replication studies, and we have substantial shrinkage in all 4 replication projects. So in psychology, it's most drastic, 0.29, but also in social science, it's 0.5, 0.67 in economics. Only philosophy there's less shrinkage of 0.86. So you may wonder, why do we have so much shrinkage? Why are the effect sizes so much smaller in the replication projects than in the original studies, and there are probably many reasons which contribute to this reproducibility crisis, and I just want to mention a few. Publication bias is certainly one of the reasons that only significant studies get published or are more likely to get published. P-hacking, so that people don't have a protocol but play around empirically with the data and just publish the results they like, the significant ones. Harking is another issue, hypothesizing after results are known. So again, without a protocol, get some data, and then maybe you see something, and then you say, well, this is actually what I intended to look at from the start. Many studies may be underpowered, which also increases the risk of false positive findings, and so on and so forth. I mean, those are kind of the things, the more general issues that contribute to the replication crisis. But going back to statistics, this substantial shrinkage suggests that methods which assume original and replication study to be exchangeable are inappropriate. And the methods I described so far, meta-analysis assumes exchangeability, the two trials rule assumes exchangeability, and they seem to be not well suited to analyze such data. So that brings me to the skeptical p-value, and this is a method I published last year in a discussion paper of the Royal Statistical Society. In a sense, it's not a 100% Bayesian method. It's a Bayes non-Bayes compromise based on two steps: a reverse Bayes step and a prior criticism step, and that gives rise to the skeptical p-value to quantify the degree of replication success. So how does this work? Well, step one is reverse Bayes. So what is reverse Bayes? Well, reverse Bayes analysis goes back to Jack Good, I.J. Good, and I think he was the first who proposed this many years ago. And in his book, Good Thinking, you'll find this quote: "We can make judgments of initial probabilities and infer final ones, or we can equally make judgments of final ones and infer initial ones by Bayes theorem in reverse." So what is really pointing out that if you look at Bayes' formula, you can read that from the left to the right. So you start with the prior, update the prior with the data to obtain the posterior, and I guess this is what we all do all day, and that's what I would call forward Bayesian inference. But there's nothing in the theorem that dictates this direction. You can also go in the other direction and start with some posterior, in a sense, subtract the data, and then obtain the corresponding prior. And that's reverse Bayes. And you'll see an application of this in a minute in the context of replication studies, but I just want to briefly point you to a recent review I wrote with colleagues Robert Matthews, Manuela Ott, and Samuel, and you can find that on arXiv with other applications of reverse Bayes methods. Okay, so how can we use this in this replication setting? So this again shows the study I showed at the beginning, but just the original one. And I changed the layout a little to have kind of one-sided confidence intervals here and one-sided p-values. And so this is my result, and we cut off 2.5% here at the bottom, so it's a significant result. And now imagine a skeptic comes into play, a skeptic who doesn't trust that result, right? So the skeptic has a skeptical prior with mean 0 and some variance tau squared. And now we apply reverse Bayes and ask the question, well, how skeptical do we have to be to make this original result, this discovery, no longer convincing? So we derive the variance of the skeptical prior such that the posterior has 2.5% quantile exactly fixed at 0. So 2.5% of the posterior mass is below 0. So basically you beat the frequentist with its own weapons, and you say, you know, if you believe in this p-value thresholding, then if I combine your result with my sufficiently skeptical prior, you know, the combined posterior is no longer convincing. And this is basically this reverse Bayes approach that you fix the posterior, subtract the data, and then you get the sufficiently skeptical prior. Now we need to bring in the replication experiment, and to do so, I would like to cite another, you know, big name in Bayesian statistics, which is George Box, and he wrote a very nice article that I came across again a few months ago in this edited volume here. I think it's from 1983, where he says the process of scientific investigation involves not one, but two kinds of inference: estimation and criticism, used iteratively and in alternation. And it's the criticism that we need now. So what do? This is the picture again I showed you, but now we've conducted the replication experiment. And in a sense, with that replication experiment, we want to show that the skeptic is wrong, right? So we want to show your prior, your sufficiently skeptical prior is unrealistic. And so the original result is actually convincing, right? And how do we do this? How do we quantify this? Well, we assess the conflict between the sufficiently skeptical prior and the replication study results. And we do this with a method that has been proposed by Box already in 1980. And he proposed to use the tail probability of the prior predictive distribution. I'm sure many of you know this method. And in the current context, that prior predictive distribution is just a normal with mean 0 and variance equal to the prior variance tau squared plus the squared standard error of the replication study. Okay, and this then defines this tail probability, which I denote by P box. Okay, in the current setting, this tail probability is 0.31, so it's pretty large. And so in a sense, there's no conflict between the prior and the replication study. We haven't been able to, you know, convince the skeptic that his prior is wrong. If we would have been able, if that P box would have been much smaller, let's say smaller than the original alpha, 2.5%, then we declare this as replication success at level alpha. So again, you know, at 2.5%, P box is 0.31, so much larger. So we have no replication success at level alpha is 2.5%. Now let's increase the level alpha and see what's happening. Let's go to 5%, and you see, you know, how these confidence intervals get a bit narrower, and you also see how, you know, how the skeptical prior gets narrower, because now we have to be more skeptical to make this original result no longer convincing at a 5% level rather than a 2.5% level. Okay, so the prior gets tighter, and as a consequence, you know, this box tail probability gets smaller. Now it's 0.21. Still larger than 5%, so still no replication success. Let's go to 10%. Then P box is 0.13. You know, still not small enough, but you see how the prior got tighter and tighter. But if we go to 11%, then actually P box, you know, is 0.11, and we would be able to declare replication success at level 0.11 at level 11%. Right, and that's basically the method. And so the trick is now to get rid of alpha, to say, well, the smallest level alpha, where alpha is P box, is is the skeptical p-value, PS. And this is obviously inspired by properties of ordinary p-values. And this is also why I called this quantity PS the skeptical p-value. Right, so okay, in this particular context, the skeptical p-value is 0.11. What are the properties of this quantity? And this is given in more detail in the discussion paper. You can always compute it, it always exists. It's always larger than both of the ordinary p-values, PO and PR. That's the first property. It does not depend on alpha, so I kind of got rid of alpha. So it's not really, you don't have to use it for thresholding. You can use it as a quantitative measure for replication success, and the smaller, the larger the degree of replication success. It can be computed analytically under standard normality assumptions, and I always have to defend myself here a little because mathematical statisticians tend to criticize this, and it's not realistic to assume normality. Actually, it's the standard assumption in all of meta-analysis, and the setting we are in here is also kind of a meta-analysis. So I think it fits very well. And of course, you can also study this method in small samples, for example, and then it gets a bit more difficult, and maybe you have to compute things numerically. But under normality assumptions, it's straightforward to do it. There are closed form expressions. And if you look at those closed form expressions, you'll see it depends on three things. It depends on the original value, p-value, or on the replication p-value. But it also depends on the relative sample size. And if you fix the p-values and increase the relative sample size, the skeptical p-value actually increases. So if your replication study was really large, then it's more difficult to convince the skeptical p-value. And this is an important point, that there's a third parameter which influences the skeptical p-value. And because of that, the relative sample size matters, indirectly also the relative effect size matters. So the skeptical p-value penalizes shrinkage, as we will see in a minute. Now I've added this last point here on this slide, and I've added this warning sign because now we really leave Bayesian territory. So this is now fully frequentist. So maybe you better close your ears if you don't want to hear this. But it's quite nice actually from a more general statistical perspective, or from a mathematical perspective, that the skeptical p-value has a particularly simple form if the relative sample size is 1. So if the two studies are of the same size, and it then only depends on the harmonic mean of the squared test statistics, original and replication. And so that gives actually rise to a new way to combine p-values, and a new way to bring different studies together into one. And this is the harmonic mean chi-squared test. And the cool thing about this is that there's actually an exact null distribution, and you can extend it to more than 2 studies, and that null distribution still holds. So if you're into this, then have a look at this paper that was published last year in series C. Right, but let's forget about frequentist properties. I deliberately omitted them from this talk. And let's think a little bit about how can we actually compare now the performance of the skeptical p-value to more established methods like the 2 trials rule and the meta-analysis. And the key way to do this is to formulate the problem in terms of the original p-value. So how convincing was the original p-value? And in terms of the 2 relative measures that I introduced already, the relative effect size and the relative sample size. And this is written up in a paper here joint with Charlotte and Samuel that will appear in Annals of Applied Statistics soon. Right, and I omit the math, but I just show you a few pictures how that works. So imagine the relative sample size is a half. So the replication study is just half the size of the original study. Each of these plots gives you the success region at standard 2.5% level as a function of the relative effect size on the y-axis and the original p-value on the x-axis, right? So you see the skeptical p-value is actually quite stringent, and the success region is pretty small. The two trials rule has this weird cutoff here at 0.025, and but also requires relative effect sizes mostly larger than 1 to achieve success, because the relative sample size is only a half. And likewise, the meta-analysis has a somewhat similar picture, but it doesn't have that cutoff at 0.025. It actually goes beyond that and is able also to, to declare replication success, even if the original study wasn't really much convincing. Okay, and what I'm going to do now is I will increase the sample size. And you see already in this figure what will happen, because there are some regions shaded here where success is never possible. And by that, I mean, even if your replication study is very, very large, it's impossible to achieve success. And this holds for the skeptical p-value and the two trials rule. And so let's see what's happening if I increase the sample size. So a half, 1, 2, 5, 10, 1,000. So what's happening here? Well, you see the skeptical p-value actually converges to this limiting line here, below which replication success is never possible. So I think it does something very sensible. It penalizes shrinkage and is not happy with replication studies that have a lot of shrinkage, even if the sample size, or maybe just because the sample size was very large, the replication sample size. The other two methods do not have that property. So for the other two methods, this bound converges basically down to 0. So you can have replication success even if your relative effect size is very, very small. And obviously, this is something we should avoid, I think. And so let's formalize this a little, and we coined that the shrinkage paradox. So every method gives the minimum relative effect size, d min, which is a function of the original p-value, the relative sample size, and the level. And the shrinkage paradox, so this is not Stein shrinkage, it's our shrinkage paradox. At replication means that this d min converges to 0 if the relative sample size goes to infinity. And there's actually a second version of the shrinkage paradox. If the original p-value goes to 0, then also, and if again d min goes to 0, then this is the shrinkage paradox. And original, actually the skeptical p-value suffers from this. You don't see this exactly so, but basically the asymptote here actually goes down to 0. But the more troublesome shrinkage paradox is the shrinkage paradox at replication, because you can basically steer that by just artificially increasing the sample size of the replication experiment. So the pictures you saw showed that the two trials rule and the meta-analysis, they suffer from both these versions of the shrinkage paradox, and the skeptical p-value actually only suffers from one. Now, just a side comment here before I move to the skeptical Bayes factor. The skeptical p-value is also too stringent, so it doesn't seem to be well calibrated, because replication success is impossible if the original study is only borderline significant. So basically we fixed that, and it's quite nice because it involves some nice mathematics and the golden ratio actually. So basically you have to multiply your set value or divide the set value by the square root of the golden ratio. details are in the paper I showed earlier. And that gives you a more liberal threshold that has a nice property, and you'll see the property in a minute. You can equivalently recalibrate the skeptical p-value such that you can still compare it to a nominal alpha level. And this is actually the default in the R package because it's kind of what scientists are used to. So what is the point of this recalibration? Well, on the left, you see again the picture that you saw earlier, where it's impossible at the nominal level to achieve replication success for a borderline convincing original result. And with the golden level, we actually make sure that this minimum relative effect size actually crosses the red point here, which is at 0.025 and a relative effect size of 1. So that means if your original study was just borderline convincing, replication success is only possible if the relative effect size is larger than 1. So that seems like a sensible requirement to say, well, if you come just with a borderline convincing study, then I don't accept shrinkage. Okay, this is the golden level. Let's go to the replication projects, and this shows the proportion of successful replications with the 2 trials rule and the skeptical p-value in the 4 projects. And what you see is that roughly the proportion is quite similar with the 2 methods. So you may wonder, when do the 2 methods actually disagree? And those are the 6 studies where they actually disagree, and they can be described as follows. The first 2 are 2 studies where, which failed to pass the 2 trials rule because either original or replication was not convincing enough, but actually the skeptical p-value is happy with it. Some actually had a larger effect size at replication compared to original. And the other 4 is just the other way around. And so those are studies which passed the 2 trials rule, but the skeptical p-value wasn't happy. And if you look at this column D, then you see the reason for that. All these studies had, a lot of shrinkage. So the relative effect size was 0.4, 0.5, 0.3, and 0.4 again. So a lot of shrinkage, which is penalized by this method. Recently, there was a paper here in Royal Society Open Science, how best to quantify replication success, and the authors compared a bunch of different methods to do this, and actually turned out that this skeptical p-value performed best with some other method, and particularly well under scenarios of high publication bias. All right, I have to move on to the next part. I hope I still have a few minutes. The skeptical Bayes factor. So let's go back to George Box. In the article I mentioned earlier, Box comments that Bayes completely solves the problem of estimation, but also can be helpful at the criticism stage in judging the relative plausibility of 2 or more models. So obviously this refers to Bayes factors, and you can compare different models with the prior predictive distribution and the corresponding Bayes factors. And the first group who did that was group around E.J. Wagemarkers, which what they call the replication Bayes factor. And recently Samuel and I tried to bring the concept of the skeptical p-value over to the skeptical Bayes factor. But let's look first at the replication Bayes factor. So that's pretty straightforward to explain. I should mention that I assume normality here, whereas these authors use more elaborate Bayes factors based on Cauchy. So in the spirit of Jeffries, but for simplicity is only normality here. So the idea is basically you use the replication result to compare the point null to an advocate. So now we have not just a skeptic, but an advocate who believes in the original result. So the advocate prior is just normal with the effect estimate of the original study and the corresponding variance. and we compare that to the point null and compute the Bayes factor. Right, so that's pretty straightforward. And the skeptical Bayes factor is also easy to understand if we understand the skeptical p-value, because basically we replace alpha levels with gamma levels, which are now on the Bayes factor scale. And we replace this prior criticism step where I was using tail probabilities earlier now with a second Bayes factor. So first we determine the sufficiently skeptical prior such that the Bayes factor null versus the skeptic based on the original data is some value gamma in 0, 1. And then in the second step, we compare this skeptic from step number 1 to an advocate, which is the same advocate as in E.J. Wartenmager's proposal, and compute the corresponding Bayes factor, BF skeptic versus advocate. And if this is smaller than the original gamma level, then we declare replication success. And we can, go even one step further and say, okay, the smallest level gamma at which replication success can be declared defines the skeptical Bayes factor, right? So it's the same idea behind it than in the skeptical p-value, but just replacing p-values with and tail probabilities with Bayes factors. What are the properties of this concept? Well, it does not always exist. It does not exist if the original study is unconvincing. You also have to make sure to deal with Lidley's paradox and these things. So details are in the paper. Don't want to mention them here. I don't have the time to mention them here. It cannot be smaller than the minimum Bayes factor for the original study. So there's always a lower bound on the Bayes factor for a given result. And so the skeptical skeptical Bayes factor cannot be smaller. And the great thing is it does not suffer from the shrinkage paradox, neither at replication and even not at original. So it's even better than the skeptical p-value in that sense. There's a closed form expression available for c = 1, but it gets more complicated than for the skeptical p-value. Here you need what's called the Lambert function. And for c not equal 1, you can calculate it numerically. So let's look again at the replication success regions, skeptical p-value, skeptical Bayes factor, replication Bayes factor. And you see in the middle, the skeptical Bayes factor, which also has kind of a cutoff as the 2 trials rule. But in contrast to the 2 trials rule, the minimum relative effect size doesn't converge down to 0. If I increase the sample size, it converges to some limit, just as the skeptical p-value does. So I think this is a unifying property of this reverse Bayes concept, that you don't have this shrinkage paradox at replication. The replication Bayes factor, which you see on the right here, actually suffers from that. So if I increase the sample size to a very large number, 1,000, then the success region actually converges down to 0. So let's look again at the proportion of successful replications. And you see skeptical p and skeptical Bayes factor actually have very similar proportions. They disagree only in 1, 2, or 3 studies, whereas the replication Bayes factor has slightly larger proportions. And that's just a consequence of that larger success region that you just saw on the earlier slide. And now, the last few minutes I want to use to show you some studies where they agree or where they disagree. This is again the study I showed at the beginning, Pick and Rawson. So you know that already. The skeptical p-value recalibrated gives me 0.061. So basically, no replication success, or not much replication success, depends a little bit how you interpret this p-value. And the skeptical p-value gives you, skeptical Bayes factor gives you 1/1.2, so also not worth bare a mention. So very weak replication success evidence. The replication Bayes factor is slightly smaller, 1/4. So if you apply the standard Jeffreys category. So that would be already moderate or even substantial evidence for replication success. So there's some degree disagreement here between the replication Bayes factor and skeptical Bayes and skeptical P. Here's another example, Janssen et al. This is a study which was, very convincing at original. So the original p-value was very, very small. A lot of shrinkage, effect size is just half. And also the replication p-value, not very small, 0.013, but still small enough to fulfill the two trials rule. Skeptical p-value is actually happy with this. 0.003 flags replication success at at standard levels, and this is because of the replication paradox at original. Because if the original study gets very convincing, if PO converges to 0, then the skeptical p-value may flag success, even if there is a lot of shrinkage. And this is exactly what's happening here. And the other two methods do not suffer from that problem. And so you see that both Bayes factor methods actually report a Bayes factor of 1/1.6. So not worth a mention. Okay. The last example I want to show is a peculiar one, really. Ranganathan and Nosek, where the original study was anything else but significant. The effect is basically 0. The one-sided p-value 0.046. I think actually the authors fell into the absence of evidence is not evidence of absence fallacy here. But anyway, they replicated that study, and at replication, actually they got something significant with an effect estimate of 0.11. So the skeptical p-value is not happy with this. And also the skeptical Bayes factor is not happy with this, because these two methods, they want to confirm an original study. But if there's nothing to confirm, then they will not flag replication success. However, the replication Bayes factor doesn't do that. And as you see, actually it's very small, 1/1000. So that would be actually, in Jeffreys terminology, decisive evidence for replication success. Right. I'm about to finish. I hope Marina gives me 2 or 3 minutes to finish up.
Yes, definitely.
Okay, thank you. So let's sum this up, and then I have 1 or 2 more slides. So take-home messages. I think standard statistical methodology is not fit for purpose to analyze replication studies, where you kind of want to take both studies into account, but you do not want to assume exchangeability. I think reverse Bayes offers a lot in this setting. And as we saw, it requires both studies to be convincing, and it avoids the shrinkage paradox at replication. So I think those are quite nice properties that these methods carry. I should mention that you can use these methods also for the design of replication studies, and we have methods implemented in the package. And so you can also design your study to achieve replication success, for example, with the skeptical p-value. And I have some backup slides if somebody's interested in this. And we have 2 packages currently: replication success with the skeptical p-value and Bayes rep with the skeptical Bayes factor. They currently, on our Forge, respectively, GitLab, but will be soon on Crown. To finish up, because I guess some of you may now wonder, well, is this now Bayesian or is it not Bayesian what this guy is doing here? I have a quote that I would like to read to you. These days, the statistician is often asked such questions as, are you a Bayesian? Are you a frequentist? Are you a data analyst? Are you a designer of experiments? I will argue that the appropriate answer to all these questions can be, and preferably should be, yes. And that we can see why this is so if we consider the scientific context of what statisticians do. So I would really, underline this quote, and you may wonder who actually said that. And if we replace data analyst with data scientist, then this quote looks actually pretty modern to me. But it was George Box in 1983 at the beginning of this chapter entitled An Apology for Ecumenism in Statistics, where he also, looks at the different philosophies in statistics. All right, some acknowledgements. I'd like to thank my university, USAH, to fund the Center for Reproducible Science, where I'm working. We also have a Swiss reproducibility network where we investigate the things that I described in my talk. And the Swiss National Science Foundation is funding our project, so many thanks to them. And here you see Charlotte, Samuel, both working on the methodology. I described Simon and Eva, they work in the center. Robert Matthews, who basically invented this reverse Bayes method that I presented, and Manuela, they participated in the review on reverse Bayes. Guido Consoni gave us a lot of expertise on Bayes factors, and finally Florian is helping with implementing this stuff on CRAN. And so thanks for your attention, and I look forward to the discussion.
All right, thank you very much. A virtual applause to you. We had a good audience all throughout. I saw numbers ranging from 84, 85 up to the peak of 99 attendees, I think.
Right.
So let's see if we have some questions. I see a couple in the Q&A. I don't know if you see the Q&A, you want to read and answer the questions, or should I read the questions to you?
I just see one question from Guido Consoni.
Okay.
Maybe you see more questions. I'm in the chat. Hold on, I need to look at the Q&A.
Yeah, no, the Q&A. So I'll read the first one while you find it, perhaps. The first one says, thank you for an interesting talk. Is your skeptical p-value invariant under swapping the order of the two trials, which I think refers to one of the examples that you showed?
Oh, yeah. Yeah, that's a good question. No, it isn't. And I think it shouldn't be, because you don't want to treat the two studies as exchangeable. So the answer is no, it's not invariant. Right. Okay. It really, it's directional, right? So you question whether the original result is credible, and then you conduct the replication experiment. So the order matters. Yes. It's only exchangeable if C is 1. So if the relative sample size is 1, so if the studies have the same size, then it's actually exchangeable. But in all other cases, no.
All right. And this question was from an anonymous attendee. Then we have a question from Chris Pachorik. Shouldn't we consider what a sufficiently large effect size is for it to be of interest in the substantive context, particularly in a medical context? This approach ignores that.
Yeah, this is a very good point, and I agree. This approach ignores what is usually called the clinically relevant difference in a medical context, and this is something we want to work on. We haven't done so far. I mean, implicitly we do it, right? So because we penalize shrinkage, and so it takes into account effect size, but it only takes into account relative effect size, the effect size relative to the original effect size. And I agree, in medical context, you may have from external sources, an effect size that really matters, and then you might want to take this into account, and this is currently not done. Good point.
All right, thank you. And then from Alexander Lee, thanks for the great talk, Leo. Do you know how the skeptical p-value and Bayes factor work under optional continuation? That is, where replication attempt 2 is started because replication attempt 1 was deemed successful, and where replication attempt 2 would not be conducted if replication attempt 1 was a failure. Have you got the chance to study the number of false discoveries in the procedure if the procedure is used en masse in this manner?
Well, that's a great question. Thanks to Alex. We haven't really studied this. I mean, I should have mentioned that, some of these replication projects actually conduct not just one replication study, but more than one. And we currently extend the skeptical p-value to the setting when you have results from, let's say, 3 or 4 replication studies, and you want to flag replication success. And Alex is right to point out that sometimes these replication studies may be conducted sequentially. And you know, as soon as you move into such a sequential setting, things get quite complicated, as we know from clinical trials and adaptive designs and all those things. So we haven't really looked at this, but it's a great question, and we'll look into this. Thank you.
All right. Next, Guido Consonni. Can you say something about the case in which the original and the replication studies are heterogeneous?
Yeah, thanks, Guido. I mean, the concept of heterogeneity is a concept which is often used in meta-analysis, that you allow for heterogeneity between studies so that the underlying true effects are not identical, but they come from a common distribution. So I think this concept is somehow linked to exchangeability still. So you still want to treat the studies as exchangeable. And I think because we have this different approach to question the original study, I think this issue is, at least in the analysis, not so important. But having said that, when it comes to design, so when you want to design your replication study based on the results from an original study, then I think it makes sense to incorporate heterogeneity in the, let's say, sample size calculation. And yes, so that would be my short answer.
All right. And finally, a question from Dan Phillips. Would you agree that there are two different questions? Whether an experiment has been confirmed to be effective, for example, does the drug work? And whether the effect size of the experiment has been confirmed, for example, how effective is the drug? Would you suggest different methods for each of these questions?
Yes, thanks for the question. I guess that relates to the question earlier about the clinical effect size, right? So whether you just check whether it's different from zero, or whether you check whether it's substantial mass larger than the clinically relevant effect size. Yeah, I mean, the methods I described do not really incorporate, as I said earlier, the effect size that is relevant in your application, really. And I think this is something you should look at, and I agree that this is something people should look at. But I also want to re-emphasize that the methods I described, they take into account the relative effect size. So basically, at least the relative effect size is taken into account. So how much shrinkage is there from replication to original? And I think this is one of the major problems that we face in these replication projects, to incorporate this feature in the analysis. But I agree, it's important to also to look at well, clinically relevant differences.
All right, so these are all the questions. I think, yes, there's one in the chat, but it's from Guido, and I already read this to you. I think, yes, it's the same question. All right, so that's great. I mean, we're perfectly on time, 12:40, at least here in Texas. And thank you again, Leo, for the great talk.
Thank you for listening, and have a nice evening in Switzerland or wherever you are, lunch or whatever. Right.
All right. Thank you. Thank you.
Thank you. Bye-bye.